this fourth article, this is September, so after the summer holiday basically, is about, well, as you probably can tell, the mass energy equivalence. Classically we say a stationary mass, so that doesn't have any velocity, doesn't have any energy, aside from, well, thermal energy or chemical energy, or basically if I lift it then it has potential energy. We don't mean that, but no energy at all. And Einstein basically said, well, it has an energy according to this formula. So any mass, even at rest, has an energy in it. Much, much more than chemical energy can provide. Much, much more. Like a factor of 1 million or something. So much, much more. And there's again the light speed. So basically he derived this from what he did before in the other article. And another reality check for you. I like these things. The whole article is only 3 pages. Right? So that's theoretical physics for you. Sometimes it's very short, very dense, and very shocking. So it has the formula, but not like you know it. So let's see if you can find it. This is the whole article. And as you can see, no references, because it didn't need it. He worked alone, right? He didn't work in a group of people. So okay. You probably won't find it because it's not there. E equals mc squared. This is the formula. I'm gonna zoom in. Okay, so that's where the well-known formula comes from. And basically it's this. You see it here. So k0 minus k1 equals L over v squared times v squared over 2. So this is the same thing, but in better font. And from this follows basically the well-known formula. So what he described is the change in kinetic energy if you move at a certain velocity. And it depends on the mass, basically. So if you compare this side to this, and that's basically half mv squared, which is a very well-known formula for the kinetic energy. So the change in kinetic energy is half mv squared. Then this L over v squared should be the mass m. And he used the capital V for the light speed. So he didn't assume that the c from Maxwell's equation is his light speed. It was, but he didn't assume that, so that's nice. And he used L for well, basically the light energy that's in mass or whatever. So he didn't use E, but of course you can follow from this formula I described it here. You can follow E equals mc squared. So if you Google Einstein images, Einstein, of course with E equals mc squared, you see all these kinds of images. So this is all not true. Basically he said this. So. But that's not how people remember that. So, of course, the formulas mean the same thing, and they used the other symbols, and they coupled it to Maxwell's equations with the C, and they wrote it just the other way. It doesn't matter. Mathematically, it's completely equivalent. So, but it's basically, it's funny that he never, in this original article, he never actually said E equals mc squared. So that's, of course, I think that's fun. Anyway, so this is something that he did in, well, basically half a year, right? We started in March, it's September now, so that's pretty good. And we have applications of this well-known formula. One of them is, of course, in diagnostics in the hospital. We use them for PET scans. So that means positron emission tomology. So basically you scan a patient. The patient is injected with a radioactive, well, fluor, for instance, and that emits a positron, so an anti-electron, also anti-particles. They are derived from a formula from Einstein, by the way. And this positron, of course, immediately hits an electron that's very nearby, and that they annihilate each other, so the two masses disappear, and two photons, two energy packages, appear. And so basically this amount of mass turns into that amount of energy. Those two photons, they are radiated exactly 180 degrees away from each other, and they are detected by a camera. And from that, and the measurements of the time, you can determine where the photons came from, and you can make a scan of all kinds of dynamic processes in the body. And we can use that, so combine it with CT scans, which is a very fancy X-ray scan, basically. And then you can see the organs and basically all the processes happening in the organs. So this is very useful, of course. Also, obviously, nuclear energy. In nuclear energy, well, what we do is, so far, is nuclear fission. So basically splitting a large atom. And in that process, if you add the masses together, you see there's some mass loss, and that mass loss is turned into energy. That energy is used to heat up water. The water, or basically turbine, you heat up water, you get steam, and that basically sets the turbine in motion, and we use that to generate electricity. So, of course, this is used worldwide in many, many places, and probably a lot more in the next few decades, I guess. And another thing, it's not a human application yet, we're working on it, but in nature the application is well known. It's called the sun, or stars. They use nuclear fusion. A different process, completely different process, by the way, which gives per process a lot more energy. So if you can generate it, you can get a lot more energy, and no radioactive materials in principle. We're working on that. It's very, very hard. In the sun, it's not a problem. In the stars, they have a lot of pressure and temperature, and you can basically push these two protons, or net 4 protons, into each other, generate, make a helium atom core, and then some neutrinos and energy. And basically, this is the only process that can explain how stars are able to give off this amount of energy for such a long time. So the sun is already shining like 5 billion years, and Earth is almost the same age. And with chemical processes, suppose the sun is one big ball of, I don't know, coal or gas, it doesn't matter. Basically, all the chemicals have roughly the same energy density. Then you can get about a few million years of life out of the sun. Well, and the Earth is already 4.5 billion years old, so that would never work. And so with nuclear fusion, you can get a lot more energy, and the sun will probably keep on shining for another 5 billion years like this. And these are all three examples of how E equals mc squared has its use. And of course, this is the most important one, because without this, there wouldn't be any life here. So.